So question, was that a useful activity? Did you learn something from it? Okay, then it was useful.
Galvanic cells, which are also called voltaic cells. So what are they? Well, galvanic or voltaic cells are devices that use a chemical reaction to create electricity.
Okay, so on page 69, you can fill that in. Galvanic cells, also called voltaic cells, which are also called electrochemical cells, are devices that use a chemical reaction to create electricity.
Specifically, the type of chemical reaction that they use is called an oxidation-reduction reaction. But we'll talk more about that later. Now, galvanic or voltaic cells may be totally new terms for you, but I'm willing to bet that you use these devices almost every single day of your life. And that's because a battery is an example of a galvanic or voltaic cell. There are chemicals inside batteries, and those chemicals react together in an oxidation-reduction reaction that makes electricity.
I'm just going to pause and see if I can up the volume a little bit.
And this is what powers your cell phone or your flashlight or whatever the battery is hooked up to. So let's learn more about these devices and see how a chemical reaction can create electricity. Okay, so I think for the rest of this video, I'm just going to call these voltaic cells instead of calling them galvanic or voltaic cells. All right? So I now want to talk about the parts of a basic voltaic
Page
cell,
69.
one that you could actually make in the lab. So here's what they are. First, we start with two beakers or containers of water. And into one of them, we dissolve some zinc sulfate to make a solution. And then into the other, we dissolve some copper sulfate and make a solution with that. So we got these two solutions. Then we take a piece of zinc metal, like this one right here, and put that in the zinc sulfate solution.
Do you remember what that's called? That piece of metal? It's an electrode. Okay, that is your electrode.
And then over here, we take a piece of copper metal and we put that in the copper sulfate solution. The next thing we do is we take a wire, a metal wire, and we use that to connect the two pieces of metal together. And when we do this, something amazing starts happening. Electrons start moving through this wire.
And one of the reasons that we're going through this is one of the things that you will be called upon to do is to draw an electrochemical cell. So it's important to know I need two beakers with solutions. I need two electrodes. I need a wire. And then he's going to introduce one more component in just a moment.
They move from the zinc metal into the copper metal. Now, this is a big deal because moving electrons are what make electricity. So when we hook this wire together with the pieces of metal and electrons start moving through it, we have electricity. We have electricity moving through this wire. And what we could actually do is we could take a little light bulb like this and hook it up to this wire, and the light bulb would turn on because there's electricity moving through this wire. Now, to be really specific, there's one more part of the voltaic cell, and that's a little tube called a salt bridge that connects these two solutions. We'll talk more about the salt bridge at the very end of this video, but right now I'm going to leave it out because I want to make sure that we keep things simple. So this is the basic setup of a voltaic cell. Now, I want to zoom in so that we can see the atoms and electrons in the metal and in the solution and understand what's causing electrons to move along this wire and create electricity. Here's our magnification of the different parts of the voltaic cell. we can see some of the atoms in the metals and in the solutions. So let me show you what's what. This is a magnification of the area here. These zinc atoms are on the edge of the piece of the zinc metal. And then these Zn2 plus ions are in the solution. They're part of this ZnSO4 solution. I'm not showing the SO4 here. I just want to focus in on the zinc. So zinc ions in the solution and these zinc atoms in the piece of zinc. Then over here,
Is he talking too slowly? He's good? Okay.
we have these Cu2 plus ions that are in the CuSO4 solution. They're dissolved here. And then these copper atoms are on the edge of this piece of copper here. Okay? So we've got a wire that connects the zinc and the copper. And we've said that when we hook everything together, electrons start flowing through this wire. Well, why is that? Well, when we connect these two pieces of metal with a wire, it kind of starts a tug of war between the zinc and the copper. They're having a tug of war for the electrons. One of them wins and one of them loses. It turns out that Cu2 plus, these atoms here, Cu2 plus has a really strong pull for the electrons.
So what kind of agent would it be good at being if it has a good pull on electrons? Chat with your neighbor about that. If Cu2 plus has a strong pull for electrons, does that mean it's a good oxidizing agent or does that mean it's a good reducing agent? If I have a good pull on electrons, I'm good at taking them away. Yes? What did I just do to her? She got oxidized because she lost electrons. So what kind of agent am I? I'm an oxidizing agent. Yes? Because I was good at taking electrons away. So I made other people lose electrons. Yeah? So copper 2 plus is a good oxidizing agent.
But then on the other hand, zinc, these zinc atoms, zinc has a weaker pull for electrons. So in this tug of war, Cu2 plus ends up winning. Let me show you how this happens. So Cu2 plus really wants electrons. So it's kind of like it calls over here to zinc, which has a weaker pull on the electrons, and says, hey, zinc, give me some of your electrons. And zinc's kind of weak, so it's like, oh, okay. And what happens is, let's say this zinc atom here gives away 2 of its electrons. And these electrons enter the wire and move towards the copper. Now, when zinc gives away those 2 electrons, it causes its charge to change. It's lost 2 electrons, so it gets a positive charge, and it becomes Zn2 plus. Now, changing from neutral zinc to zinc 2 plus has a big effect on this atom. And that's because neutral atoms make up solid metal, but metal ions usually dissolve in water. So after this zinc atom,
what's going to happen to the zinc? If neutral atoms make up solid metal, but metal ions usually dissolve in water, what is going to happen to this zinc, which lost 2 electrons? It's going to dissolve in the water. Watch it go.
turns into Zn2 plus because it lost these electrons. It's no longer part of this solid metal anymore, and it floats off, it dissolves into the solution. Okay, so that's what happens to the zinc. Then, over here, these electrons make their way down the wire to the copper, And one of these Cu2 plus ions, which really wants electrons, is going to come over here, and these 2 electrons are going to be added to the Cu2 plus ion. Gaining these 2 electrons is going to get rid of that 2 plus charge that was on the copper. And that is going to turn it into a neutral atom, which means that it is no longer going to be able to dissolve in solution, and it's going to become part of the solid copper metal here. Okay? So that's what happens to the copper. Now notice that for this whole process to happen, electrons have to move through this wire, and that's where the electricity, the electron movement, comes from. Let's see that one more time. So zinc loses 2 of its electrons here. Those move through the wire. Loss of those 2 electrons causes zinc to take on a 2 plus charge. It is then going to dissolve in the solution. These 2 electrons are going to move over here to copper, and one of these Cu2 plus ions that really wants electrons is going to come, it's going to take them in, and that is going to get rid of the Cu2 plus. It's going to get rid of the 2 plus charge, and this neutral copper atom is now going to become part of this solid piece of copper metal.
So just while we're here, take a look at what's happening. We have Zn turning into Zn2 plus. What process is taking place at the zinc electrode? The zinc is turning into zinc 2 plus. Chat with your partner about that. What process is taking place here? Zinc is turning into zinc 2 plus. I'll give you a hint. It's either oxidation or reduction. Which one is it? Zinc is turning into zinc 2 plus, and it's sending its 2 electrons over to the copper. Zinc is turning into zinc 2 plus. It goes from zinc 0 to zinc 2 plus. What process is that? Oxidation. And it sends its 2 electrons away from it. So what process is that? Oxidation, right? So over here we have oxidation. Do you remember what we call the electrode, the piece of metal where oxidation occurs? It's the anode. Do you remember how to remember it? Anox cared. Okay? Anox cared. Did you see the little picture of the little ox on the picture? Like, it was really cute. Do you know how long it took me to find an ox? Where is it? With a little heart on it? Right? You know, that's not something that we just, have floating around. Where was it? It was here somewhere. Oh, no, it's in here. There we go. Okay. Where is it? An ox cared. See? A little ox with a little heart. Okay. Anywho, back to our video. Now over here, we have our other electrode. We have the copper electrode. What process is taking place here? The electrons are coming into the copper, and they're joining up with the copper 2 plus. What process is taking place here? Reduction. The Cu2 plus is turning into Cu0. What do we call the electrode where reduction takes place? That's called the cathode. Okay, that's the cared part. Cathode is reduction. Anode is oxidation. Cathode is reduction. You can do anox cared. When I was in high school, I was just like, A and O are both vowels. C and R are both consonants. So that was like a really easy way to remember it also.
So that is where this electron movement through the wire is coming from. Zinc loses these 2 electrons. They move through the wire, creating electricity. They come over here and they join up with the Cu2+, turning it into neutral copper. We have these electrons moving through the wire here, creating electricity. So that is how we get electricity, from these electrons moving from the zinc over here into the copper. And if this happens long enough, we actually see these 2 pieces of metal change, right? Like these zinc atoms keep coming off of this piece of zinc, so it's essentially dissolving. And over time, what we'll see is that this piece of zinc actually starts to dissolve. It gets smaller and smaller. But then on the other hand, those Cu2+ ions are coming out of solution and are attaching to the solid copper. And so they're going to make this piece of solid copper bigger and bigger. And so if we let this voltaic cell run for long enough, we'll eventually see that these 2 pieces of metal actually change size and shape. Here's some
so let's just go back to that for a second. I just wanted to point out to you that this is something that happens in all galvanic cells. Well, not all of them. There's some where it doesn't, because this doesn't involve a metal. But in any one where you have a metal, and a metal being the half reactions, the anode will get smaller as it gets oxidized. You take the solid metal, the 0 charge metal, and it becomes an ion and dissolves away into solution. And the cathode always gets bigger and heavier, because those positive ions glom onto it, grab 2 electrons, and become solid. And I like to think of it like fat cat. Cathode gains mass, and that means that the anode loses mass. So fat cat.
Eventually see that these 2 pieces of metal actually change size and shape. Here are some diagrams for the process that's happening in the voltaic cell. I want to describe what's going on in terms of oxidation and reduction. So over here, one of these neutral zinc atoms is losing electrons. So that means that oxidation is happening on this side of the voltaic cell. And over here, this Cu2+ ion is gaining 2 electrons to turn into a neutral copper atom. So reduction, or gain of electrons, is happening over here. Now, we can give names to these 2 parts of the voltaic cell based on whether oxidation or reduction takes place. So the cathode is the name that we give for the site of reduction, where reduction happens. So reduction is happening here, which means that the piece of copper is the cathode, the site of reduction. And the piece of zinc over here is where oxidation is happening. So the piece of zinc is going to be the anode. So
if you are looking for where the heck are we are on page 72, and you can fill in the little diagram there. The piece of zinc is the anode. And what happens there? Oxidation. The piece of copper is the cathode. And what happens there? Reduction. Excellent.
Reduction at the cathode on copper, oxidation at the anode on zinc. Now, let's write reactions for the 2 processes that are happening here, okay? First, let's write the reaction for reduction. We're starting with Cu2+, and this Cu2+ is dissolved in solution. So I'm going to write that with an AQ for aqueous after it to show that it's dissolved in solution. Now, this Cu2+ gains 2 electrons, so I'll write plus 2E-, and that gives us a neutral copper atom. So I just write Cu with no charge after it. That shows that it's neutral, and then it's part of the solid metal, so I write an S after it. So this is the reaction for the reduction process. Over here, the reaction for the oxidation process. We start out with a neutral zinc atom. And this neutral zinc atom is part of the solid piece of zinc. So I'm going to put this S here for solid. Now it loses 2 electrons. To show that we lose something in a chemical reaction, we put it on the other side of the arrow. Okay? So I'm not going to write anything right here. I'm going to put this arrow. I'll leave the electrons for last. Losing the electrons turns the neutral zinc atom into a Zn2 plus ion, Zn2 plus, that is now dissolved in solution. So I'll write AQ here. And then finally, to show that I lost those 2 electrons here, I'll put plus 2E minus on this side. So this is the reaction for the oxidation. Now these 2 reactions that I wrote, we call them half reactions because each one of them tells half the story of the oxidation reduction process.
So this whole thing is a cell. So each half, each beaker is a half cell. Okay, so you have the oxidation half cell and the reduction half cell. So we've actually physically separated the oxidation from the reduction, which is so cool because then the electrons have to go from the wire, go through the wire, and then we can harness that electricity. Love it. So exciting.
And we can actually give names to these 2 parts of the voltaic cell as if each one of them is half of the big picture. We call this the oxidation half cell. It's half of the voltaic cell where the oxidation is taking place. And we call this the reduction half cell. It's half of the voltaic cell where reduction is taking place.
So you can fill that in on the diagram as well.
That show what's going on in each one of the half shell, in each one of the half cells. I said half shells. It's like Teenage Mutant Ninja Turtles coming back to haunt me from the 80s. Anyway, we have these 2 half reactions, and we can put them together to get a net ionic equation, which shows the overall oxidation and reduction process.
And do you notice we have our electrons going out, equaling our electrons going in, and then he added them together, and you get the full redox reaction. Now, we are out of time, so your homework is to finish 6.2D and finish watching this video. You're not expected to do the questions for this one, okay? Because we want to talk about a few things before you get going on that, all right? So just finish watching. You might have to skip by some stuff that I threw in the middle, okay? Finish watching this, finish filling in, and finish 6.2D. Excellent. Excellent. Thank you. Thank you. Very good. Thank you. Awesome. Thank you. Thank you. Wonderful. Awesome. Thank you. Oh, wonderful. Thank you. I will check you off on that. See you later. Bye.
I guess